Hey everyone, welcome back. So today we're diving straight into the secrets of password security. Now we've touched on basic hashing before, which is kind of like putting a strong lock on your data. But today we're adding the magic ingredient, salting. If hashing is the lock, salting is what makes every single lock completely unique. Because without it, even the most advanced hashing algorithms leave your systems dangerously vulnerable to pre-computed attacks. Over the next few minutes, we're going to completely demystify both the why and the how of password salting. Here's the roadmap for this explainer. We're going to hit the unsalted hash problem, what a salt actually is, defeating rainbow tables, generating and storing them, doing implementation right, and finally, some common salting mistakes. By the time we wrap up, you'll know exactly how to secure user credentials the right way.
All right, section 1, the unsalted hash problem. Let's talk about the very real danger of identical hashes.
To really get why salting is so absolutely crucial, we've got to understand the problem. Picture this. You're storing passwords. You're using a solid algorithm, maybe bcrypt. Now, imagine two completely different users. Let's go with Alice and Bob, and they both just happen to choose summer 2024 as their password. So what happens when they hit submit? Well, without a salt, both of those hashes in your database are going to be completely 100% identical. And that's a massive problem. It means if a hacker cracks just one of those hashes, they've instantly got the password for both users. And that perfectly illustrates the flaw here. Identical passwords equal identical hashes. But here's the thing. Attackers, they don't sit there cracking these one by one. No way. They use what are called rainbow tables. Think of a rainbow table as a massive pre-computed database that maps common passwords straight to their hash values. It's a classic time-memory trade-off. If you're not using salts, an attacker literally just does one quick lookup in their table, and boom, they've instantly compromised every single account in your database that used a common password. One cracked hash, thousands of compromised accounts.
Moving right along to section 2, what exactly is a salt? Enter the savior of password security.
So what is it? A salt is just random data. It gets appended or prepended to a password before it goes through the hashing function. The key here is that every single user gets their own unique salt. Remember Alice and Bob with their identical summer 2024 passwords? When they log in now, the system adds Alice's unique random data to her password and Bob's unique data to his. So even though they typed in the exact same password, the resulting hashes that you actually store in the database, totally, completely different.
Now, I want to clear up something that confuses a lot of developers. Salt versus pepper. It sounds like cooking, but it's crucial cryptography. A salt is unique per user. It's stored right alongside the hash in your database, and its main job is to defeat those rainbow tables we just talked about. A pepper, on the other hand, that's a shared secret value, added to every password. But, and this is a big but, it has to be stored completely separately from the database, like in a hardware security module. It adds what we call defense in depth. Basically, if someone steals your database but not your app server, they still can't crack the passwords. But honestly, peppers add a ton of operational complexity. Like, if you lose your pepper, every single user password is suddenly invalid. Because of that headache, OWASP doesn't even include pepper in its core recommendations. So, let's just focus on getting the salt right first.
Section 3, defeating rainbow table attacks. Let's look at the math that makes this work. 208 billion. Now, in everyday life, that's a massive number. But in cryptography, it is actually terrifyingly small. 208 billion combinations is roughly all it takes to pre-compute a rainbow table for an 8-character lowercase password. For a modern attacker with some decent hardware, calculating and storing 208 billion hashes is a walk in the park. It's highly manageable. And that right there is why unsalted databases are such easy pickings. The attacker builds the table once, and they completely own your users. But let's contrast that with 2 to the 128th power. This is where the mathematical magic of salting really shines. When you add a standard 16-byte salt to a password, an attacker can't just use their single pre-built rainbow table anymore. Because the salt is unique for every single user, the attacker would have to pre-compute a totally separate rainbow table for every single possible salt value, meaning they would need 2 to the 128th power different tables. Guys, that is literally more rainbow tables than there are atoms in the observable universe. It takes rainbow tables from being highly manageable to completely computationally impossible. You've just forced the attacker to manually crack each user's password individually. Game changer.
Okay, on to section 4, generating and storing salts. Let's get into the practical rules.
This is where I see developers reach for the wrong tool all the time. Please never ever use standard math random functions like math.random. They are not cryptographically secure because their outputs are actually predictable. What you absolutely need is a cryptographically secure pseudorandom number generator, or a CSPRNJ. The exact command depends on your language. In Python, you're going to use secrets.token_bytes16. In Node.js, it's crypto.randombytes16. And over in Java, secureRandom.nextBytes. These specific functions pull true entropy from the operating system, stuff like disk timing and hardware interrupts, which gives you genuinely unpredictable bytes.
All right, we really need to debunk a massive myth right now. Salts do not need to be kept secret. They are stored in plain text right there alongside the hash. Honestly, if your database gets breached, it's completely fine if the attacker sees your salts. Why? Because a salt's job is uniqueness, not secrecy. Its whole purpose is just to force the attacker to crack every password one by one. And another thing, you should never store a salt in a separate database column. Actually, doing that is a major code smell. It usually means you aren't using your modern cryptographic libraries correctly, which brings us to
Section 5, doing implementation right. And the golden rule here, don't roll your own crypto. In production environments, we constantly see developers taking the completely wrong approach. They try manually concatenating a salt with a really fast algorithm like SHA-256. Now, SHA-256 is designed to be blazingly fast, which is the exact opposite of what you want for password hashing. And simply adding a salt yourself doesn't magically fix that speed issue. The right way? Use modern purpose-built libraries like bcrypt or argon2id. Look, if you are currently writing string concatenation code to combine a salt and a password, you need to stop immediately. And if you've inherited legacy code doing this, take a deep breath. It is totally fixable, but it definitely needs to go. Because the beautifully simple truth is that modern libraries make all of this completely effortless. Libraries like bcrypt and argon2 do all the heavy lifting for you. They automatically generate those proper 128-bit salts using a secure random generator behind the scenes. Then they embed the salt, the algorithm version, and all the parameters directly into one single, neat output string. When that user logs in later, the library just automatically extracts the salt from that string to verify the password. That's why you don't need a separate column. Ultimately, this entire super complex cryptographic process gets reduced to just two simple function calls in your code, one to hash and one to verify. That's it.
Finally, Section 6, common salting mistakes. Let's look at a few pitfalls to avoid. I'm going to rapid fire through these, mostly because if you use a modern library correctly, you'll avoid all of them automatically. First mistake, reusing the same salt for every user. Just don't do it. It entirely defeats the purpose and brings those rainbow cables right back into play. Second, using predictable data like a username or an email address as the salt. Salts must be completely random. Third, generating short salts from weak random sources, like those basic math functions we talked about earlier. And finally, the big misconception we already busted, treating salts like secret encryption keys. Say it with me. Salts are about uniqueness, not secrecy.
Okay, time for a quick knowledge check to make sure this all stuck. Question 1. What is the core difference between a salt and a pepper? Question 2. Why exactly is a 16-byte salt the recommended standard? And question 3. If you find manual SHA-256 salting in your codebase, how do you actually fix it without breaking existing user logins? I'll give you a second to think about it.
All right, let's see how you did. For number 1, a salt is unique per user and stored with the hash, while a pepper is a shared secret kept entirely separate. For number 2, those 16 bytes guarantee 2 to the 128th power possible combinations, which makes precomputing rainbow tables computationally impossible. And for number 3, and this one is super crucial, you fix manual SHA-256 by migrating to bcrypt or argon2 using what's called the progressive upgrade pattern. You do not force a massive, annoying password reset for everyone. Instead, the next time a user successfully logs in, you quietly verify their old SHA-256 hash, then you immediately rehash their plaintext password in the background with argon2 and overwrite the old entry. It is a seamless, secure migration, and your customer support team will absolutely thank you.
So I want you to think about your own code base right now. Ask yourself, if your database leaked today, would attackers be forced to calculate hashes until the end of the universe? Or did a lack of proper salting mean they're already logged in? Salting isn't just a nice-to-have best practice. It's the absolute baseline of modern password economics. Thanks so much for joining me on this explainer, and stay curious.